Yeah, okay, so welcome back everyone. So today it's my pleasure to welcome Francesco Ferrini, who will be giving the fourth lecture of the hands-on introduction to graph deep learning. So today we'll be talking about heterogeneity and knowledge graphs. Yeah, thank you.
So thank you for the introduction. Welcome everyone. Today is the last of our 4 talks on hands-on introduction to graph deep learning with examples in PyTorch Geometric. I am Francesco, and my talk of today will be about heterogeneity in graph neural networks, and in particular how graph neural networks are able or can model and incorporate information from graphs when where the type of nodes and edges is different. So when we really have heterogeneous graphs. So I organized the talk of today in these 5 in this schedule. So I'll explain what's an heterogeneous graph and why it is important, where it is actually used, and then we will pass to the more practical part. So graph neural networks, a brief recap about graph convolution, and then we will talk about the relational graph convolution that is also called heterogeneous graph convolution, which is a specific graph neural network for heterogeneous graphs. And then I would like to finish by talking about, let's say, 2 future directions. So the first one is metapath learning for graph neural networks. And then since we saw that you were interested, some of you were interested in knowledge graphs, we will have some final slides on knowledge graphs, opportunities and open challenges on this type of heterogeneous graph, because at the end it's just an heterogeneous graph, but let's say bigger. So let's start. So first of all, I'm introducing again what's an homogeneous graph. So far you have seen graphs where the graph had only one type of node and edge. So here we can have still features on edges and on nodes, but the type is always the same. So you are not considering the type of node and edges. But are all graphs of this type? Of course not. We can have heterogeneous graphs. Heterogeneous in the sense of node types. So here on the right, you see a graph where you have 2 types of nodes. So node of type E, which can be, for example, paper nodes, and node of type and node of type B, which are other nodes. And you see that the color is not really a feature at the moment, but consider it as really as a type. And then we can increment the complexity by presenting the types on relations. So here we have 4 different relation types. So for example, the green relation is a relation from an author node to a paper node, which of course means that an author has written a particular paper. Still on the same couple of node type pairs, we can have an author that likes paper with orange relation type. Then with brown one, we have an author that collaborates with another author, like here, for example. And last one, a paper that cites another paper. So we have a red node connected to another red node. So this is really a possible heterogeneous graph. Very simple one, because we only have 4 relation types and 2 node types, but still is the very simple heterogeneous graph. Now we can define formally what's a heterogeneous graph, and is defined in this way. So we have a graph G, where we have a set of nodes V and a set of edges C. And until now, you have already seen this formulation with homogeneous graphs, right? And so what's the difference? The difference is that we also have these 2 mapping functions, so tau and phi, where tau is a mapping function that specify the type of a node given a node, and phi is the second mapping function that specify the edge type given a specific edge. Okay, so Now, what you're looking at are some real-world heterogeneous graphs. So on the left side, we have, for example, a heterogeneous graph for a biomedical application. So the colors or the name on the nodes represent the different node types. So we have nodes of type gene, disease, symptom, side effect, anatomy, etc. And we have the different relation types that connect these nodes. And you see that, for example, from a node type disease, you can have only one relation type to a node of type anatomy, which is localized, right? Instead, for example, from an order of type anatomy, you can have 3 different relation types to a node of type gene. Here on the right, we have another example of an heterogeneous graph where we have other node types, for example, a person node, a picture node, and other type of nodes like time. And all those nodes are connected by different relation types, right? As you can see. Here we have other 2 possibilities. So, for example, on the left side, we have a recommendation heterogeneous graph. So you have 2 node types, which are user and item, and they are connected. They can be connected only by these 2 relations, which are click or buy, which are the possible action that a user can perform with an item. And then we have this very famous example, which is from PyTorch Geometric library, that is a paper author institution heterogeneous graph, where we have 4 different node types and also 4 different relation types. So till now, I said that the type of the node is very important, but you may ask, what's the difference between the type and the features, right? It's true that you can take a heterogeneous graph, like the first one I showed you before, so where you have 2 node types, the red, which is the author, and the blue, which is the paper, and you can convert in an homogeneous graph with some binary features that indicate the type. So, for example, 1, 0 indicate blue nodes, and 0, 1 indicate a red node, right? You can still have this transformation, so you can transform a heterogeneous graph in a homogeneous one in this way, but it's not a very good idea for essentially 2 reasons. The first one is that different node types can have different length in feature vectors. So, for example, an author node can have a feature vector of length 10, for example, while a paper node has a feature vector of a different length. And so you should really aggregate information with this on these nodes in different ways, so with different models. And another reason is that different relation types represent different type of connection between nodes. And so it's really important that we specify different models for different relation types. This is because the relation type has really important semantic meaning that if you only consider it as a feature, then you may lose this information. So since we have it with an heterogeneous graph, we can use it, of course. So at the end, what we can say is that heterogeneous graphs are more expressive. Okay, so now we do a brief recap of graph convolution. That is what you have essentially seen in the other lectures. So we have an homogeneous graph, an homogeneous input graph, and we want to run a graph convolutional network to update the representation of the target node 1. So we have a target node, and we want to update his representation with a graph neural network. So in this case, we are looking at a graph neural network with 2 layers, but let's concentrate first on the first layer of the graph convolutional network. Again, in this case, we are considering an homogeneous graph just to then show the difference with a heterogeneous graph convolution. So we have a target node number 1, and how the convolution works. Essentially, you are node number 1 aggregate information from its one-hop neighbors. One-hop neighbors are node number 2, because it's directly connected to node number 1, node number 3, and node number 4, right? Because all of them are connected to node number 1. And how the aggregation works, essentially you have an aggregation aggregator operator that you have also seen in the code session of Antonio, which could be like sum, min, or max. So it should be an invariant operation. And then you have some neural networks, which are essentially parameters, learning parameters that are shared in this layer, because we don't have types on the relations, right? So we aggregate information from these 3 nodes, node number 2, 3, and 4. And if we go one step further, so if we consider a second graph neural network layer, we reach the 2-hop neighbors. So we aggregate information from the nodes that are 2-hop neighbors, of target node. So in order to update the representation of node number 1, we aggregate information from all these, let's say, path of nodes. Okay, this was for graph convolution, but what happens if we consider an heterogeneous graph convolution? So convolution for an heterogeneous graph. So here you have the same example, but with an heterogeneous graph. So in this case, consider the fact that you have different relation types. So we have relations, green relations, purple, and brown, for example. And in the first layer, you still aggregate information from the neighbors, from the one-hop neighbors of node target 1. But in this case, you see that what is really changing are the neural networks, so are the parameters of the network, the parameters of the layer. Why? Because since node number 2 and node number 3 are connected with a green relation to node number 1, we want some specific parameters for the green relation. Instead, for node number 4, we want other parameters that are not shared with these 2 nodes, because he has a different relation type. So essentially what's happening here is that we are aggregating information. Node number 1 is aggregating information with different parameters depending on the relation type. If we go one step further, again, exactly like before, you have is there a question? Nope. Okay. You have in the second layer, you are getting information from the 2-hop neighbors, but in this case, you have other weights or other matrices of parameters, depending again on the relation type. So what we can understand here is that at the end, for each layer of the network, we will have a different matrix, different weights for each of the relation type. So this is essentially what's happening in this layer here. So we are aggregating information, we are updating the representation of the target node. So in this case, node I is node number 1. We are aggregating information from its one-hop neighbors, but specifying matrix of parameters specific for the relation type. So if we have 10 relation types, we will end up having 10 matrices of parameters, right? And of course, we also have the self-loop. So we also aggregating the node number 1, also aggregate information from itself, and this is called the self-loop. You have also seen this in the previous sessions. So again, we are updating the representation, but differently with respect to the classical graph convolution. You are specifying parameters for each relation type. Of course, this aspect has a problem, because if you start having a high number of relation types, you will end up having a very huge number of parameters. And the solutions for these are essentially two. So one is called block diagonal matrices. The other one is basis learning. Now, for the sake of simplicity, we are we will see only the basis learning, also for the code session in which we will see what's really happening with this basis learning. So in basis learning, just it's important that you just understand the very basic idea. You are the problem is that you have too many parameters, too many matrices of parameters, and so you want to decrease this number. How you do it? You essentially specify some PB, which are parameters shared across all relations, and so you have this matrix BB, which is shared. So all the relation types will have this matrix of parameters, and then you have one coefficient specified for each relation. So the only parameter that is really specific for each relation type at the end will be this one, this AR, which is simply a coefficient. Okay, so at the end you will finish having a fewer number of parameters with this basis learning. Okay, so now before the coding session, let's see what we are essentially, which is the task we are trying to solve, which is node classification. So we have an heterogeneous graph, like the one on the left. So we have different relation types. Each node has a particular class, and which are the training nodes. So we have labels on these on those nodes, and we want to predict the labels on the unlabeled nodes that are the test nodes. And we want to do that using a relational graph convolutional network. Okay, so this is essentially what we are going to see in a few moments with the code. So now let's go to the code. Okay. Okay, so I hope you are seeing my screen. Okay. Okay, so first of all, we start with some imports. We are going to use PyTorch Geometric and PyTorch, and Network X, which is a library to draw and do some simple operation on graphs, and Matplotlib for visualization. Then you have also seen this before. It's just because if we have GPU available, so we may want to speed up the code, we can use this, and we can specify that the device on which we want to run the model and where we want to put our dataset is a GPU. Otherwise, of course, we will use our classic CPU. Then what we are going to do now is to create a very simple heterogeneous graph, but just for visualization. So first of all, we create the edge index, which is a tensor of this type, where we are simply saying that node 0 is connected to node 1, node 1 to node 0, etc., etc. So at the end, node 5 with node 1. And also on homogeneous graph, you have this type of edge index. What is different is with respect to homogeneous graphs is the type of the edge that we are specifying here. So essentially is again a tensor where the length of the tensor is the same of the one before, where we are specifying the type of the relation between the two nodes. So node number 0 and node number 1 are related with relation 0. Node number 5 and node number 1 are related by relation 2. Then we will specify the our data object again from PyTorch Geometric. In this data object, we specify the edge index and the edge type. Then we create a graph with Network X, and then we have to add stuff on this graph, of course. Indeed, we are adding the nodes on this graph with adds nodes from, with add nodes from function from network X. Then we need to specify which are the colors we are going to use. And for simplicity, since we know that there are only 3 relation types, which are 0, 1, and 2, we need only 3 different colors, which are red, green, and blue. And then we use the classical function that I think you have already seen for drawing the graph and plotting the graph. And at the end, you will see that you obtain this visualization in which different colors represent different relation types. And at this moment, we do not consider different node types because as you have seen in relational convolution, heterogeneous convolution, it's more important to distinguish between relation types. Okay, so we can go one step further and download a real-world dataset for a real-world heterogeneous graph, which is a dataset from entities of PyTorch Geometric, which is named AIFB. And if we look at the dataset, you have already seen something like this. So we have the edge index, we have the edge type exactly like before, and then we have the train IDs, which are essentially the IDs of the training nodes. We have the train Y, which are the labels, so the classes of training nodes. We have the test IDs, which are the IDs of test nodes, and test Y, which are the labels of test nodes. And then we also have this num nodes parameter. Then with this torch.unique, we are going to see which are the classes of our dataset. So each training node can be either of class 0, class 1, class 2, or class 3. And this is exactly what we want to learn. So we want to create a graph neural network that is able to distinguish, to learn which is the class of each node. We can also see which are the relation types in our dataset, which in this way. So we are taking the unique values of data of the edge type of our dataset, and you see that there are 90 relation types in this case. So quite a high number, let's say. Okay, so since the dataset is quite big, in order to simplify things, and we can with this k-hops subgraph, we can reduce the graph by considering only the 2 hop neighbors with these 2 value here, the 2 hop neighbors of training and testing nodes. So all the other nodes will be discarded and won't be used in the training. So we can recreate the dataset object, and indeed you see that with respect to before, we have a different edge index, which is smaller, and also we have a different number of nodes, which again is smaller because we have discarded all the nodes that are more than 2 hop far from the test and training nodes. Okay, so now we have finished with the dataset. So now we can instantiate our model, which is our class called heterogeneous network from module, which is the base class for all neural network modules in PyTorch. And what's important here, that is essentially what you have also seen before in my slides, are these 2 relational graph convolutional network layers. Okay, so we have these 2 layers, which that wants input dimension, which in this case, since nodes in this graph don't have features, we can also specify the number of nodes in the graph. Then we have the hidden dimension that is specified before, which is the dimension we want to, is a hidden dimension of the network. Then we have the last parameter, which is the number of relations. And why we want to specify it is because our RGCN layer, our relational graph convolutional network layer, at the end, and we'll end up creating one matrix of parameters for each relation type. So we have two of these layers, and then in a forward we will use this layer in this here, and then we will add nonlinearity with the ReLU function, just as in the formula on the slide. And then we will have the second relational graph convolutional layer here. We have to specify the same stuff as before. And at the end, what is returned is the log of the softmax of the x-axis, which is the output. And the softmax is essentially a function that converts a vector of real numbers in a vector of probabilities, essentially exponentiating each value so that it will be positive, and normalizing by the sum of the exponentials. So you will end up having a probability for each class, and of course the higher. So if the probability is higher for class 0, means that a node has been learned to be of class 0. Okay, then we can instantiate the model, and whether we have a device, we can put the model on a device. And if we print it, you see that it has essentially two layers. The first one, where we have specified the number of node types, the number of nodes, sorry, and the hidden dimension, and the number of relations. In the second one, we have that from a hidden dimension, we reach 4, which is the number of classes, right? Because at the end, again, we will have a probability for each of the classes, for each node. Okay, so then we can go one step further, and we reach the training procedure, which is done as usual. So we have a training and testing, and we train the network for 30 epochs because it's quite simple at this point. What's important that is in the training, we have the optimization procedure, which calculates essentially the loss between the predictions and the actual true labels, and then the loss is back propagated as in usual machine learning procedures, so that the network can change the parameters and learn the parameters in order to have a better accuracy. Indeed, if you see what's happening in the training loop, you see that the loss is decreasing, while the accuracy, both in training and also in testing, is increasing. Here we only need 30 epochs to reach a quite good accuracy, right? You see it. Because the graph at this point is quite simple. What is important to mention here is that if we look at the model parameters, if we look at the shape of the model parameters, we see that in the first layer we have essentially 90 matrices of this size, so 6,909 by 16, where 6,909 is the, let's say, input feature dimension, and 16 is the hidden feature dimension, and 90 is the number of relation types. So we have 90 of these matrices, which is a very high number of parameters, right? But then what we can do is to apply basis learning. So what we have just seen in the slides. So essentially this heterogeneous network is exactly like before. The only parameter that we are specifying is the number of bases here, which is the number of shared matrices in between different relation types, and this is done again for reducing the number of parameters of the network. The rest is exactly like before, so we can simply go at the end by checking the fact that the accuracy is still the same in this case, which means really that the dataset is simple. But what is changing is that the number of parameters is different with respect to before. Because if we now look at the weights, at the parameters of the first layer of the network, we see that we, instead of having 90 matrices of this size, we only have 30 matrices of this size, right? So we have really reduced the number of parameters. In this case, the performances were like before because the dataset is simple and for other reasons. Of course, if you reduce so much the number of parameters, you can have problems instead in terms of learning, because of course you reducing too much the number of parameters can decrease the performance of your network. Okay, so now
I have a question.
Yes, please.
So, but how are you choosing now the number of bases? Because you say if you choose too much, you reduce too much, you have some problem. But how do you choose them then?
Thanks for the question. Actually, for this hands-on, I just selected a number which is very smaller with respect to the number of relations in the graph. But this number of bases is essentially an hyperparameter, so it's something that you should learn during your training, and you should like try to change this parameter and see what are the effects on the accuracy of the network, on the accuracy, of course, on the loss decrease, and of course, so you can at the end set your the best value for basis for your particular dataset. So essentially, you should try with different values, see what's happening in the training set, and then applying on this number on the test set.
Okay, thanks. Makes sense. Yeah.
Perfect. Okay, so if there are no other questions, I can go back to my slides. Okay. Okay. Okay, so till now, what we have seen is that we can, yes, specify different parameters for different relation types, but when you start having very complex graphs where the number of features is high, the number of relation is higher with respect to what we have seen until now, we still have a problem of parameters because you cannot reduce too much the number of them, otherwise you start having problems in performance, right? So what's next? Quite new research area on heterogeneous graph learning is graph neural network applied based on Metapath. So let's start explaining what are essentially Metapath. So they are chain of node and edge types in a heterogeneous graph. So if you have a graph of this type where you have 3 types of nodes and you have these 4 types of relations, so you can have a relation from 5 types. Sorry, you can have this red relation from actor node to an actor node. You can have this purple from an actor node to a director, the blue one from movie to director, etc. This black one from director to director. You can extract some meaningful chain of relations and node types, like this one here. That is a path from an actor node to a movie node, and from a movie node to a director node with their specific relation types. Okay, So this structure is a meaningful structure, and of course, in order to extract it, there are different ways. But why they are important? They are important because if you have a graph where you have thousands of relation types and node types, you can use a graph neural network that aggregates information only through this metapath. So if you have a target node that is a director node, you can aggregate information only based on the metapath that I've shown before. So the first layer, you aggregate information only from moving nodes, and in the second layer, you aggregate information from the two hop neighbors based on a metapath, so from the outer nodes. Okay. There is an extensive literature on metapath and graph neural networks. The problem is that most of these approaches are based on predefined metapath, which means that there is some sort of domain expert, so a person that really knows the dataset and that knows which are the meaningful metapath on this dataset. And the other problem is that many of these approaches are built for graphs where the number of relation types is quite small. So a solution, of course, would be to learn these metapath graphs where the number of relations is high, of course. And for example, here we have a figure from a work that I will present next week at the Learning on Graph conference. Essentially, you still have an heterogeneous graph where you have different type of nodes, which are defined by the shapes. These nodes can have color, which is a feature of the node. So a movie node can be a drama node or a comedy node, and a director node can be an award-winning director or not award-winning director. We have 4 different type of relations, and what we want to do is not extract, but learn metapath in order to make classification on nodes that have a label. So we have pentagons nodes that have a label, plus or minus, and we want to learn metapath that are able to, with a graph neural network, that help a graph neural network to learn the labels of pentagons. So just in a few words, we have a heterogeneous graph and a scoring function that extracts some candidate metapath, and then these candidate metapath are given to the metapath graph neural networks, which is this one, and with the initial dataset, we can make prediction on the dataset, and at the end we can learn the meaningful metapath. So in this case, we do not need a domain expert to understand which are the meaningful metapath, and also since what the scoring function is doing is selecting which are the best relations in this way, then you also can use this approach on datasets where the number of relations is really high. Indeed, the results in brief are really that this metapath graph neural network works in synthetic cases, also increasing the complexity of the graphs, has similar performances with state-of-the-art approaches in real dataset where the number of relations is small, and it's better when the number of relation types is high. Okay, so now we are going to have an extra session on knowledge graphs, since we saw that you expressed interest on this topic. So we can start by explaining what are knowledge graphs. And knowledge graphs are essentially heterogeneous graph, but they comes from real world concepts, indeed, and they represent real world knowledge in this structured way. So we can have entities that are the nodes of the graph, and represent real-world concepts. We can have relations that connect entities, and the relations have a semantic meaning. And then we have facts that are triplets, and they are built with an head entity, a relation type, and a tail entity. Here, I left you some sources on some real knowledge graphs. So you have, there are really many of them. Here is a really small example related to the free-base knowledge graph, where we have 5 type of nodes and 6 type of nodes and 5 type of relations. So we have movie nodes, director, year, actor, production studio, genre type, and of course we have different relations for each of them. So you see here that in knowledge graph, most of the time, the feature of a node are encoded with relation and other node. So for example, the year in which a movie was published could be also a feature of the node. Instead, in a knowledge graph, is represented with another triple, and so in this way. So in these graphs, these graphs will end up having thousands of relation types. And indeed, one possible example is this triple here. So the film Inception that was published. So we have the first entity, the relation type, pub year, and the year in which it was published. So the second entity, which is of the type year. Okay, so these are some statistics of some of the knowledge graphs that I've shown you before. So this is just to explain very briefly that the fact that it's really important to work on knowledge graphs because there are really thousands of entities and thousands of relations. So for example, you take Freebase here that have 50 million of entities and approximately 3 billions of triplets, which are 3 billions of relations. And there are also a high number of relation types, right? And it's the same thing for all the other knowledge graphs. So you see that a problem in existing knowledge graph that represents the real knowledge can be, for example, the fact that there is some missing knowledge in the graph, so there are missing connections, for example. This is just one of the classical problems that may arise in knowledge graph. Indeed, there are really many challenges, really many research fields on knowledge graphs. The most important for machine learning are, of course, knowledge graph embedding, in which the neural networks are used to encode entities and relations, so that the embedding of each node and each edge can be helpful for the task of, for example, predicting a missing link or to classifying the class of a node. And here you see other fields in which knowledge graphs are very useful. I would like to say that graph neural networks are not used. It's not the most used approach for knowledge graphs. There are many approaches, of course, and graph neural networks are still used, but there are other type of approach that don't use graph neural networks, but use other type of neural network or in order to learn from these structures. So here there are. I left you some real interesting surveys on knowledge graphs. I really find them interesting. So if you are interested, you can look at them. I also left you the link. And just to conclude my talk, what we have seen is that also in graphs can have heterogeneity in nodes and edges, and you can deal with this with graph neural networks, with a specific type of graph neural network, which is called relational graph convolutional network. This type of graph neural networks have a problem, which is the fact that the number of parameters increases when the number of relation types increase. This problem can, of course, be solved by some metapath graph neural networks that focus only on relevant paths in heterogeneous graphs. And then we finished just discussing a bit about what are knowledge graphs and some challenges that are still open in knowledge graphs, some fields that are in which knowledge graphs are studied. And I will leave in a few days also the code of knowledge graph embedding on the GitHub page that where you find all our material. I didn't do it for today because for the sake of time we didn't have time to explain this. But of course, if you have any question about it, you can ask. You can write me, or you can write me, and we can have a chat about this, of course. So thank you very much.
Yeah, thank you very much. Thank you. Yeah, any questions, comments? Yeah, I think he said like next. Yeah, someone is asking about the notebook when it will be shared, but I think he said in the next few days. Yeah.
Yes, exactly. Yes.
Yeah. All right. I think so. No, everything was clear. No questions. Thank you again. Thank you very much for today's talk and for the entire series. I'm sure that everyone appreciated it. As I told you, I already got a lot of good feedback about it. So as I said, the invitation is welcome. If you have like other extra material, you are always welcome to come back and then have an extra session.
May I ask a question?
Yeah, sure.
Yes.
Yeah, I'm very impressed by all this set of tutorials, and I'm tempted, after learning them carefully, to figure out some problem that I may encounter. And the question is, will this framework or template be useful to deal with examples that are not discussed here? Namely, it may come not only in my research, but in other people's research. So how easy it will be, or hard, to translate a problem like that to this wonderful 4 tutorials. We probably heard 3 or 4. I cannot even follow. There is so much. It's overwhelming, and I appreciate the talent of the speakers, and of course, thanking Boumediene.
Thank you very much for the question. Well, actually, you can think that we presented some hands-on that take a graph and make some operation on graphs in order to learn some something on them. Like for node classification, you can learn with a neural network, graph neural network. You can learn the class of the graph. With in graph classification, you can learn the class of the entire graph. And so whether you are able to transform any type of structure in a graph, so an homogeneous or heterogeneous graph, you can use these tutorials. You can use these hands-on that we presented in order to apply these tutorials, these graph neural networks on your data. I don't know if I answered your question some way.
Oh, yeah, my question is a little bit too general. But
so I think I have something concrete. Is that
yes, I have something concrete.
Yeah, if you have a problem, like a concrete problem, we can just discuss about it as a researcher together. Because the Gabriele is a good friend.
So I will challenge you. I will challenge everybody.
Yeah.
There is at Cornell an expert in building structures of struts and chains and so on. And I forget now his name because I'm too busy with so many things. But it's called Tesenergy or Tenergy. You know the right word for it. When you build a structure, okay, like a toy, and you calculate the tension or the stability of that structure. Now, all this can be, I believe, projected as graph. And it will be very exciting to do this kind of, because these people develop all kinds of high-level mathematical theories, but in practicality, whether that bridge is stable or not can be, theoretically at least, intuitively, be solved by your system here. And so the lazy person question is how I translate. Like, I don't want to build your system from scratch. I want to be able to translate it, a problem that I may have, or even in biology, to translate it to this kind of, collection of techniques, let's call it.
Yeah, someone wrote the word like called tensegrity. Yeah, I'm aware actually of people who are using it for biology. Actually, we have a talk on graph neural networks in biology in early January by someone from Imperial, and she has been working on this kind of techniques specifically in biology. And the next week's speaker, actually, she's going to give a talk, and then her expertise is also graph neural networks in medical imaging. So maybe if you come next week, you can ask her about application in medical imaging. But if you have specific problems in this tensegrity, I mean, you can reach out to us, right? And me and Gabriele and then the four speakers, and maybe so maybe we can just look at it all together, right?
Okay, wonderful.
Yeah.
Thank you so much.
Yeah, thank you. Yeah, thank you. All right. So, any other questions or comments? All right. Okay. Thanks again, Francisco, and then thanks again, everyone. As I mentioned, there will be a talk next week, like slightly related to GNN, but like another one, like an application of GNN, will be in early January by Islam, I think. Yeah. Okay. Thanks everyone, and have a good day. Yeah. Take care. Bye.
Thank you very much. Bye bye.